Okay, we are back. So we have this question, example five. We have 12 candidates running for three leadership positions. The top vote will be elected mayor, second will be deputy mayor, and the third will be treasurer. So one way we can do this is that there are three positions: mayor, deputy mayor, and then treasurer, right? So there's 12, and then once the mayor's decided, then there's only 11. Once the deputy mayor's decided, now there's 10 options. So this is just 12 times 11 times 10, and that's it. Okay, so that's one way to do it. Sorry about that. I was just trying to see if we pop this in. 12 times 11. I was trying to see if my brain would work, but it was not. So what, 1320, 1,320 options. Cool. Or we can do the formula. So the formula, let me change colors for effect. The formula, which is NPR, we know it's a permutation because order matters, right? It matters who's mayor, it matters who's treasurer, right? So the order matters. The order matters. So N is 12 because it's a pool of 12 people, and R is 3 because we're doing the 1, 2, 3 position. This is 12 PR. Oops, excuse me. P3 helps if I can write. So you can do the math, or you can grab your handy dandy. Probability, NPR, that needs to be 12. There we go, probability, and then 3, 1320. Or by hand, the equation says that it is 12 factorial over 12 minus 3 factorial, which is 12 factorial over, let's see, 12 times 3 is 9. So this is 12, 11, and 9 factorial over 9 factorial. Anything over itself is 1. So bingo, boom. We get the same thing. Either way you do it. So either of the three ways, totally cool. Now for combinations. Combinations are for whenever all selections come from a single group. So we still have to have it that it comes from that single pool, right? Like we can't be like picking people from all sorts of different places. Then no item can repeat. So yeah, it can't be taken more than twice. So far, this is the same thing for permutation. So far, same thing. The big difference is that the of order of arrangement does not matter. It's really hard to write in all caps. Does not. Oh, that says dose. Sorry. There we go. Y'all used to that by now, though. Who are we kidding? So even the word arrangement, I kind of like shied away from using it, but basically order does not matter. That's what I want you to take away. Order does not matter. Okay, combination order does not matter. So rather than electing mayor, I almost said depot, depot mayor, so like deputy mayor, treasurer, you're just like a committee of 3 people. Okay, committee of 3 people. So the formula for calculating combinations, because order doesn't matter, if I had like the order of 2, 3, 7, or 372. These are the same thing under combination. Combination, there we go. Okay. Under combination, those are the same thing. 237 or 372. So we have to divide out more. We have to divide out, we have to take out the duplicate, things that are now considered duplicate. For permutation, these are totally different options because order matters. Now that we're a combination, these are the same thing. So we now have to divide out more options because again, things like this are thought of as the same. So when, excuse me, how is this read? It's the number of combination of n items taken are at a time. Sometimes also said n choose are. Okay, sometimes also just n choose are. Next page. So basically from here on out, it's a bunch of examples, y'all. Okay, just a bunch of examples. 8 students, James, Dora, Maria, Leo, Gary, Tyler, Casey, and Henry are members of the science club. 4 of these students are randomly chosen by drawing names to judge a science fair at a local middle school. What is the probability that James, Maria, Gary, and Tyler are chosen without regard to order? A, and then that should be B. What is the probability that James, Maria, Gary, and Tyler are chosen in that order? So I would really like for you to just pause and try it on your own. Like really think about it, see what's what. And then once you've thought about it or given it a shot, press play. So here, since the order doesn't matter, this is combination, right? Combination. So there are 8 students and we are choosing 1, 2, 3, 4 students. This is 8, choose 4, or 8 students chosen 4 at a time. This is 8 factorial, or 8 minus 4 factorial. And then we have to divide out the things that are now similar. Right, so it says without regard of order. That means Tyler, Gary, Mary, James, the same thing as this order right here. This is 8 factorial. Divided by 8 minus 4 is 4. So 4 factorial, which is 8 times 7, 6, 5 times 4 factorial. Y'all know anything over itself reduces out. This is 8, 7, 6, 5. Oops, don't need that dot there. Pardon me. It's 4, 3, 2. Well, 4 into 8 twice. 3 times 2 is 6, so that disappears. So this is really just 2 times 7 times 5, which is 10 times 7 or 70. So there are 70 ways that we can choose these 4 people. Okay, there's 70 ways we can choose these 4 people. We cannot really do the 1, 2, 3, 4 slot anymore because of the fact that the order doesn't matter. Okay, so that kind of option's out the window. Now, what is the probability of James, Maria, Gary, and Tyler in that order are chosen? Oh, excuse me, what's the probability? Keyword probability. Well, the probability of, let's say, JMGT is equal to, remember, it's part over a whole. There's only one way to get this order. It's JMGT. That is 1 over, what's the whole? There's 70 options. That is 1/7. 70th probability. Ta-da! So here's where this is where we marry the probability with the counting. So what's the probability of blah, 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 blah happening? All right. Suppose you select 3 different flavors of ice cream at a shop that carries 12 flavors. How many flavor combinations are possible? Note that we are not interested in the order in which we pick the flavors. That's because if you think of like you have a bowl of ice cream, here's your bowl, if we have vanilla, chocolate, strawberry here, you're like my toddler and you're like, no, I want strawberry, chocolate, vanilla, then I would just like rotate his bowl, right? So it's all in the same bowl. Order doesn't matter. And it even says combination order does not matter. So 2 for there. All in the same bowl, combination order doesn't matter. Couple ways we can think about it. You can think it in terms of it as its formula. So there are 12 flavors and we want a 3 scoop. That's the combination of 12 chosen 3 at a time. So this is 12 factorial divided by 12 minus 3 factorial over 3 factorial, which is 12 factorial, divided by, let's see, 12 minus 3 is 9 factorial over 3, which is 12 times 11 times 10 times 9 factorial over 9 factorial times 3 times 2, because that's what 3 factorial is, right? What's anything over itself? 1. Those 9 factorials are disappearing. And then, well, 3 times 2 is 6. 6 goes into 12 2 times. So I'm just going to call this 2 times 11 times, oops, excuse me, 10. Or 22 times 10, which is 220. Cool, right? You can totally put this in your calculator. I don't care. The main part is that you are choosing, you recognize that, oh, this is a combination. So you go probability. Oh, actually here, sorry, pardon me. Oh, click there. I need my 12 probability over to NCR, enter, and then I'm choosing 3 scoops of ice cream, so 220. Do that there. Sorry. Or if you have this kind of calculator, so 12 math over to probability, and then NCR, the third one. And again, 3 scoops of ice cream, 220. Ta-da! So either way, awesome. Let's keep going. Okay, now we are doing cards. Okay. How many different 5-card poker hands can be dealt from a standard 52 card deck? What is the probability of the 5 cards being a royal flush of hearts? So that is specifically a card having ace, king, queen, jack, and 10 of hearts. So you have like the top 5 cards. Okay. You have the top 5 cards. Well, in this case, the cards you have in your hand, right? If you have poker, the order doesn't matter. They're all in your hand. Okay. So first order of business, order does not matter. The cards in your hand matters. The cards in your hand are the cards in your hand. So we have to recognize, oh, okay, so that means combination. Awesome. So there's only one way to get an ace, king, queen, jack, and 10, right? Just one way to do that. So my probability of ace, king, queen, jack, 10 is 1 over, but 1 over what, right? There's only one way to get this order. That's that order. So now we need to bring in our whole. Well, how many different ways can we get any card or any 5-card hand? How can we get any 5-card hand? Well, that's 52 chosen five at a time. Okay. It's again combination because the order doesn't matter. So there's 52 cards in the deck. I have a 5-card hand. Combination because order doesn't matter. So I'm just going to pop this into my calculator. Oh, turn it on. 52 math over to probability. NCR 5. Ooh, lots of different ways. So that's 2, 5, 9, 8, 9, 6, 0. Now, about 2.6 million. That's a lot. Okay. So the probability, that goes there. The probability of a royal flush, say ace, king, queen, jack, 10, is 1 in 2,598,960th. Okay, or 1 in that. That is not very likely. Why it's a pretty impressive hand when you get one. Okay, so now this is when you are kind of the ands and ors, if you would. Okay. You're in charge of making the food choices to be served on a buffet at a dinner sponsored by a club. You are involved in on campus. The catering service offers 8 appetizers, 6 mains, 4 breads, and 9 desserts. You have been assigned to pick 5 appetizers, 3 mains, 2 breads, and 4 desserts. How many ways can you select a buffet? How many ways can you select a buffet? Well, this is really just an and, because I need appetizers and main and breads and dessert, right? Even the word and is right there. The word and tells us multiply because it has to happen simultaneously. I need all of these out on the table at once. It's not you get bread or dessert. It's not you get appetizer or dessert. It's not main or something. It's all of them. And because you have choices, and the order in which they're on the table doesn't really matter. Or if I have here's my table, here's my app, my main, my bread, and then desserts, right? Well, they're all on the table. My app options are all right here. My main option, my bread option, my desserts are all on the table. The order doesn't matter. So we know that that's a combination. And again, I have apps. So that is 8 appetizers, but we're choosing 5. 8 apps, but we're choosing 5 times a choice of 6 mains, but we're choosing 3. 4 bread options, but you are just going to choose 2. And there's 9 dessert options, but you're picking 4 of them. So it's these individual combinations at the same time. So you're just going to multiply all of these together. So I've got 8. Where is my probability? Oh gosh. Sorry, y'all. So 8, so choose 5 times 6 math probability, choose 3 times 4, oops, math probability, choose 2 times 9 probability, and CR, choose 4. Okay, so we're multiplying them all together because I need them all out on the table at the same time, which is 8, 4, 6, 7, 20. So 846,720 options. Were ways that you can do this. Isn't that crazy? That's a ton of options. You probably wouldn't think you had that many. Okay, I'm gonna start a new video so this isn't crazy long.